This is the fourth lecture and the topic is network theorems. In particular, today we propose to talk about Theorems and Nortons. We started in a very simple manner in the last lecture, stating the Theorems theorem. We want to go today in a more comprehensive manner. Both of these theorems, Theorems and Nortons, have something to do with equivalence of networks. That is, two networks N1 and N2, two networks N1 and N2 are said to be equivalent if their terminal behaviors are the same. Networks, as you know, terminal behavior of a network is characterized by its voltage current relationship. If the voltage current relationships of two networks N1 and N2 at the terminals are the same, then the networks are said to be equivalent. In particular, Theorems and Norton's theorems have to do with one port equivalence. Equivalence of one port networks, that is one port means the network contains only two terminals. Very simple one ports can be thought of like this. Let us say two resistances R1 and R2 in series, then you know that this one port is equivalent to a single resistance of value R1 plus R2. Agreed? On the other hand, if I have a one port in which two resistances are in parallel, then you know that a single resistance is equivalent to this, whose value is R1 parallel R2, is given by R1 R2 divided by R1 plus R2. These are examples of very simple equivalences. To take this further, we know that if two inductors are in series, then a single inductor whose value is equal to the sum of the two inductors is an equivalent network. If two capacitors are in series, C1 and C2, then the equivalent network consists of a single capacitor of value C1 C2 over C1 plus C2. Capacitors add when they are connected in parallel. All right. Now, Theorems and Norton's theorems go beyond this. They say, let us consider a network N which not only contains resistors, we are considering basically resistive networks, linear resistive networks, along with DC sources. This is our consideration at the present moment. We are not admitting inductors and capacitors. Suppose we have a network N which not only contains resistors but also contains voltage sources and current sources. All right. So, we are considering a composite one port which contains resistors, voltage sources, current sources, and these sources could be either independent or dependent. What we mean by dependent we will consider a little later, but what we are considering is a one port network N which contains resistors and sources. Let us use a single term, sources. Sources could be voltage or current, sources could be dependent or independent. The meaning of dependent sources, as I said, we will illustrate first, then we shall go into the explanation. What is important is that you understand the concepts. Thevenin's theorem says that if there is a network N which is linear connected to another network, let us say N1, which could be either linear or non-linear, it does not matter. N1 is an arbitrary network which is also in one port, and capital N is the one port which drives N1, that is, capital N is the driving network and N1 is the driven network. This is driving and this is driven. Then as far as the current injected into N1 is concerned, in so far as the load or the driven network is concerned, the network N or the driving network can be replaced by an equivalent network, and this equivalent network consists of a voltage source Vt, an ideal voltage source, in series with a resistance Rt. This is Thevenin's theorem. Thevenin's theorem says that if a linear network drives a load, this load could be linear or non-linear, it could be any combination of resistors and sources, but the driving network has to be linear, and the driving network, in so far as the load is concerned, in so far as the current injected into the load or the voltage appearing across the load terminals is concerned, the driving network can be replaced by a very simple equivalent network which consists of a series connection of a voltage source Vt and a resistance Rt. The subscript capital T is for Thevenin, is the first letter of Thevenin, Thevenin.
So this is only for resistive.
We shall extend it to inductive and capacitive networks later, but let's understand the concept with reference to a resistive network. We shall require slightly different techniques for networks containing inductors and capacitors. This we shall consider later. Now, to be able to understand this a little more in the perspective, let us say that under the actual network connection, let us say the load current is IL. If IL is going, then IL must come out also. All right, this current, the current coming out must be IL. Let us say that the current is IL. Then Thevenin's theorem says that if this equivalent network is connected to the same network N1, then the current here will also be IL. This is what equivalence means. Equivalence means that the terminal behavior is the same. That is, if this voltage is VL, then this voltage shall also be VL. This is what equivalence means. All right. The interpretation of Vt and Rt are as follows. We have taken a network N which contains resistors, voltage sources and current sources, and you want to find out its equivalent, you want to find out its Thevenin equivalent Vt plus minus and the Thevenin equivalent resistance Rt. Vt is simply the voltage appearing at the terminals of the one port with the one port open circuited. In other words, no current. The one port N does not drive any current. Under that condition, whatever the voltage is called Vt. So it is the Vt is the open circuited voltage. That is, when it is not connected to any resistance, the resistance is infinite between the two terminals, the voltage that appears across this is the Vt, and Rt is the ratio of Vt to the current that flows when these two terminals are short circuited. That is, N, the terminals are short circuited. So this is ISC, the short circuit current. The ratio of the open circuit voltage to the short circuit current is RT. This is one interpretation of RT. The other interpretation is that RT is the resistance looking back into N. RT is the resistance measured across this one port with the voltage sources short circuited, that is voltage sources replaced by a short circuit, and current sources replaced by an open circuit, that is like this. That is, you open the current sources and short the voltage sources inside N. Under that condition, whatever resistance is measured across the port is RT. This is the interpretation of RT, and this is where the concept of dependent and independent sources arise. Let me make a formal definition. A dependent source is one. Now we are talking of dependent and independent sources. What I have said about short circuiting a voltage source and open circuiting a current source applies only to independent sources. In finding RT, dependent sources should not be touched. Dependent sources should remain intact. Question is, what is a dependent source? A dependent source is one whose voltage or current, a source is either a voltage source or a current source. A dependent voltage source is one whose voltage depends on some current or voltage at some other point in the circuit. Alright, a dependent source is one whose voltage or current depends on some other voltage or current in the circuit. That's the simple definition of a source, a dependent source. For example, if I have, let's say, a voltage source Vs in parallel with a resistance, let's say R1, then we have another resistance R2, then I have, let's say, current source, another resistance. Suppose this is my circuit where this current is I1 and this current source is, let's say, beta times I1. Agreed? Beta times I1. Then this current source is not an independent current source, because the current generated by this beta I1 depends on the current at some other point in the circuit, depends on the current through R1. You understand this? This voltage source Vs, for example, is an independent voltage source because it generates a voltage Vs irrespective of what happens to the rest of the world. It doesn't care. Whereas this current generator is not so independent. Its current, the current generated by this source, depends on another current at some other point in the circuit, that is I1. You understand what you mean by dependent and independent sources? A dependent source generates a voltage or current irrespective of what happens to the rest of the world. A dependent source is not as free as this. Its current or voltage depends on some other current or voltage. It is not necessary that a current source should depend on another current. It could depend on another voltage. As you can see here, I can write I1 as Vs by R1, and therefore I could write this as gamma Vs, where gamma is beta by R1, and therefore this current source could depend on either a voltage or a current. Similarly, a dependent voltage source could depend on either a voltage or a current. And the important point that we are mentioning is that in finding RT, the Thevenin equivalent resistance, as I said, it is the resistance looking back into N, the network which you are trying to replace, with the following modifications. That is, if you have a voltage source, you short circuit this. If you have an independent voltage source, you short circuit this, which means that physically you remove the source and put a short circuit. If you have a current source, independent current source, you replace this by an open circuit. so that what you really do is physically remove the current source, whereas if you have a dependent voltage source, dependent sources do not touch, they are protected by a shield. You do not touch them, they remain as they are. Alright, this point has to be borne in mind. It's the most important point. This is where most of the circuit analysis, particularly by non-electrical engineers, goes wrong, and therefore you must remember this very carefully. Dependent sources cannot be touched, they are barred. Yes.
So give us an example of an independent current source.
Independent current source. Oh, that's very simple. A transistor output behaves like an independent current source. Well, we will come across circuits which can be considered as current generators. All right, electronic circuits basically. It's not as simple as a battery.
So
Yeah.
previously, while discussing Kirchhoff's laws,
Yes.
you had given a current source that sends out 3 amperes. That's independent.
That's independent. But suppose it was 3 times V1, where V1 is some other voltage somewhere else in this circuit, then it would have been a dependent source. A current source is not available in the laboratory. In the laboratory, what you get are batteries or the mains current source, the mains voltage source. These are all voltage sources. Fortunately or unfortunately, the generators that one makes in practice are voltage generators, but one can make current generators, and you shall come across circuits in future when you deal with transistor circuits which behave as current generators. We will consider them at a later point of time. So the point that I had made is that one port, a linear one port containing resistors and sources of two kinds, current and voltage, sources of two different characters, dependent or independent, can be replaced insofar as the driven network is concerned by an equivalent circuit consisting of a simple series connection of a voltage source and a resistance. And we have called the voltage source as capital V subscript T, and the equivalent resistance is capital R subscript T, and capital VT is the open circuit voltage, and to determine RT one can proceed in two ways. That is, one can find out the equivalent resistance by making some changes in the sources, in the independent sources. That is, independent voltage sources are to be short circuited, independent current sources are to be opened, dependent sources not to be touched, to be left intact. Then you measure the equivalent resistance, that is RT, or the other thing that you can do is forget about touching any of the sources. You simply find out the short circuit current. Then VT by ISC is RT. All right. Now, before we take an example to illustrate this, I want you to understand the significance of RT in another way. N can be connected to N, the network which we are trying to replace by a Thevenin equivalent, can be connected to, let's say, a resistance RL load. Now, if N is equivalent to VT and in series RT, then the current in the load in either network should be the same. If this current is IL, then this current should also be equal to IL. All right. Now, if IL is 0, under what condition does that happen? If RL is infinite, that is, if the network is open, then if RL is infinity, then you see the voltage VL, let's say, would be equal to simply the open circuit voltage, which by definition is VT. So, VL is VT. Okay. If RL is 0, that is, if this is short circuited, then the current in the original network is ISC, and in the Thevenin equivalent, what is the current? It is Vt divided by RT, because RL is 0, and therefore RT is simply equal to Vt divided by ISC. All right, this checks with our interpretation of RT. RT can be measured in two ways. You can either find out the short circuit current, or you can find out the equivalent resistance looking into this. To illustrate Thevenin's theorem, if you have any questions, I would like to answer them now before I take the example.
So does the load network have to be consisting of only resistances, or it could consist of anything?
Well, the only constraint is it must pass a current. It should not be an open circuit. That's all the constraint. It could be linear, it could be non-linear, it could contain resistors, inductors, capacitors, I don't care. But since we are considering direct current sources, DC sources, even if there is an inductor, the inductor behaves as a short circuit. If there is a capacitor, the capacitor behaves as open circuit. So basically, with DC sources under equilibrium condition, it behaves as a resistive network. We shall extend all these concepts to RLC networks at a later point of time, but we would like to grasp this concept with resistive networks first. Any other question? The example that we are about to do, we have already done in the last lecture when we solved a network containing a voltage source and a current source. We find out the currents in all the branches and so on. The same example we will take, and we shall solve by applying Thevenin's theorem. And it is not a trivial exercise, so I would like you to follow the steps very carefully. The circuit is the following. We have a 50 volt source along with two resistances, 12 ohm and 2 ohms, a third resistance 5 ohm, and a current generator of 3 amperes here. Then there is another resistance here of value 10 ohms. This is my circuit. And to make things a bit more complicated, to make it look really complex, let's find out the current through these 2 ohms. And let's call this current as I. Now, it's the same exercise that we had taken to illustrate KCL, KVL, loop analysis and node analysis. We want to solve it by applying Thevenin's theorem. All right. Now, the first thing we do is to find out the Thevenin equivalent. We call these points as, let's say, A and B. To find out Thevenin equivalent, we would like to find out Vt and Rt. To find Vt, we must open this up. In other words, our new circuit to find Vt shall be like this: 50, 12, then A and B, these are opened, then 5 ohm, and you have a 10 ohms here. In addition, you have a current generator 3 ampere here. What is Vt? Vt is the voltage difference between A and B. If we call this voltage as VA and this voltage is VB, then Vt is this difference with this polarity. Why this polarity? Because the current was assumed from left to right. So this is the polarity. If you connect a 2 ohm here, obviously the current will go from left to right. Is the point clear? We are going to calculate now Vt. Obviously Vt, as I said, is equal to Va minus Vb. So let's find out what is Va. You see that in calculating Va, we have a current source here, 3 ampere. What can this current source do? It can only drive a current through the 12 ohm here. It cannot flow in any other direction. This is the only freedom it is left to it, and therefore it will cause a voltage drop across 12 ohm of 36 volts. 3 times 12, 36. With what polarity? Plus here and minus here, right? the polarity would be plus here and minus here, and this battery is plus here and minus here. So can you tell me what VA is? VA is obviously 36 plus 50 or minus 50? Plus minus, so 86 volt. Okay, VA is 86 volt. Now I come to VB. VB is the voltage across this 5 ohm resistance. Agreed? And you see the configuration. This can be done by inspection. 50 volt is connected to a series combination of 10 ohms and 5 ohms. So very simple voltage division takes place, and it is 5 divided by 10 plus 5 times 50. Agreed? Is this point clear? 50 volt appears across a series connection of 10 ohms and 5 ohms. Remember, this is open, so the rest of the circuit does not interact with it at all. So 10 ohms and 5 ohms, what we are trying to find is the drop across 5 ohms. And obviously voltage division, R2 over R1 plus R2 multiplied by 50. Is this point clear? How much is this? 50 divided by 3. Agreed? And therefore VT, our Thevenin equivalent, is simply 86 minus 50 divided by 3, which is equal to 3 times 6, 18, 1258 minus 50 divided by 3 is equal to 200 divided by 3 volt. I beg your pardon, 208. This is VT. Now we want to find out RT. Let's find RT by both ways, both interpretations. That is by finding the short circuit current and also by measuring the resistance, equivalent resistance. It turns out that the second approach, namely finding out the equivalent resistance by killing sources, that is by killing which sources? Independent sources, that turns out to be easier. As you shall see right away, our circuit was 50 volt, 12, then I beg your pardon, this would be a short circuit now. That 2 ohm would be a short circuit. You have a 3 ampere source here, 3 ampere source, then you have a 5 ohm and a 10 ohm here. Let me draw it again. I was feeling lazy. I have a 50, 12, 3 ampere, and this place of 2 ohms which was open circuited for finding VT shall now be short circuited. This is A, this is B, and this current is the current that we are interested in finding out, ISC. Alright. Then I have the 5 ohm resistance, and this resistance is 10. Alright. I can find out ISC like this. Suppose I consider this current as I1, then ISC obviously shall be equal to 3 plus I1 by which law have we applied? KCL. Alright. We also have to know this current. Let's call this as I2. Alright. Then how many unknowns are there? 2, just 2. So let's express everything in terms of ISC, and we write 2 loop equations. Alright, 2 loop equations. So the first loop is 50, 12, 5. Agreed? Then I get 50 is equal to 12 I1 plus, what is this current? I2 plus ISC, 5 I2 plus ISC, and the other loop equation is this 10 and 12. obviously 10 I2 shall be equal to 12 I1. Is that easy to see? It's the same difference of potential. Either you apply KVL or you argue like this, these are the same 2 points, and therefore 10 I2 should be equal to 12 I1. Now I will leave the algebra to you. I have done the algebra and I leave the algebra to you. I will only give you the final result. What you do is you replace I1 by 3 minus ISC and solve for ISC from these two equations, either by substitution or by Cramer's method, I don't care. The final result is that ISC is equal to let's see, I did it somewhere, 208 divided by 46 ampere. This is the final result. My VT was equal to how much? 208 by 3 volts, and therefore my RT shall be equal to what? 46 by 3. 46 by 3 ohms. Alright. Now if you ask me now, what did we gain by Thevenin's theorem? It didn't look like a much simplified one, because for ISC I have to solve 2 loop equations anyway, isn't it? It turns out that the other method, instead of calculating ISC, the other method is a better choice here, that is finding out RT. Let us see how that solves the problem. What we have is 50, 12, A, B. This is where we have to measure RT between A and B. After killing the sources, we will see how to kill them. This is 5, this is 3 ampere, and there is a 10 ohms here. Okay. In the previous method, what I did was I short circuited this and found out ISC, the short circuit current. Now we shall argue like this, that RT is the resistance between A and B with independent voltage sources short circuited. So this is replaced by a short circuit now, and independent current sources open circuited. So break this up, remove this source physically. What are you left with? You are left with a 12 ohm in series with a parallel combination of 10 and 5. Isn't that right? Yes. What you have is 12 ohms, then a 10 ohms here and a 5 ohms here. This is the equivalent circuit. You are measuring the resistance between these 2 points. So RT is almost obtained by inspection. It is 12 plus 10 parallel 5, which is 50 divided by 15, which is equal to 12 plus 10 by 3, which is 46 by 3. This is what we had obtained after a bit long calculation in the ISC method, the short circuit current method. Nevertheless, the short circuit current has its own importance, as we shall see a little later. Now therefore, our Thevenin equivalent circuit, you remember our original problem was this: 12, 2, 5, 3 amps and 10. This was 50 volt. We were trying to find out I. This is my load, and what I found out is that my VT is 208 divided by 3 and RT is 46 by 3. This point is A and this point is B. A and B. This is my equivalent circuit. Then I connect the 2 ohm. The current through 2 ohms must be the same as in the original circuit. So what is the value of I is 4 amperes. Yeah, that's correct. and it checks with what we found out by loop analysis or node analysis. This is a non-trivial application of Thevenin's theorem, and I wanted you to know that even a complicated case like this, where there is a voltage source, there is a current source, and it's a fairly complicated 1, 2, 3, 4 resistors, can be solved by simple application of Thevenin's theorem. Now next I shall take another example which contains dependent sources and see how to apply Thevenin's theorem there. And this example, as you shall see later, is an equivalent circuit for a transistor. But just look at it the way I am drawing it now, forget about what it represents. We are interested in solving this problem. There is a dependent current source beta I1 in parallel with a resistance R2, and this drives a load RL. Alright. What we are interested in is, let us say, the current in RL. If I know if I know the current in RL, then I of course know the voltage in RL. Alright. This is what I wish to find out, IL. By application of Thevenin's theorem to that part of the network which is to the left of the dotted line. Alright. I wish to find out the Thevenin equivalent, and for that the first thing I do is to find out Vt. Alright.
Where is I1, sir? You didn't show I1.
I didn't show I1. I1 is this current. I1 is this current. Thank you. Now obviously beta I1 is now a dependent source. So let's see how we solve this problem. The first thing to do is to find out the open circuit voltage. Let me draw the circuit again. This is R1 and this current is I1, R3, beta I1, and there is a resistance R2. This voltage is Vt. Open circuit. RL is disconnected. This is the open circuit. Now to find out Vt, what are you going to apply? There is a voltage source, there is a current source, and to complicate matters, the current source is a dependent one. It depends on another current at some other part of the circuit. The simplest method, or you can think of loop analysis, node analysis, you can think of branch currents and loop currents and so on. The simplest method obviously shall be node analysis, because there is only one voltage which is unknown, and this voltage is this node voltage. After all, these two are the same nodes. So all that you have to find out is Vt. So you write one KCL equation, that is sum up all the currents that leave this node Vt. Obviously these are Vt by R2, this is the current through R2, plus beta I1. Beta I1 leaves this node, but what is I1? I1 is Vs divided by R1. So beta Vs divided by R1, alright, plus Vt plus the current through R3. There are three currents that you have to take care of, this one, and this one. These are the three currents leaving the node, and the sum of them should be equal to 0. So the third current, the current through R3, is Vt, this potential, minus Vs divided by R3. So Vt minus Vs divided by R3, and this should be equal to 0, which immediately gets you what is Vt. If I use this symbol 1 by R equal to G, capital G, then Vt can be written in one stroke, that Vt times G2 plus G3 shall be equal to Vs, I take them to the right hand side, G3 minus beta G1. Is that okay? Is that alright? Where I have used Gi as equal to 1 over Ri. Gi obviously is conductance. What is the unit? Or mhos, M-H-O-S. Alright. The Americans prefer Mohs because Siemens was a German. If Siemens was an American, they would have said Siemens. And you study American textbook. Smith is an American textbook, so he writes Mohs. Right. There are minor differences, but obviously you can see that Vt is given by Vs G3 minus beta G1 divided by G2 plus G3. All that we needed in solving this problem, in finding out Vt, was KCL, KVL and common sense, which is the strongest tool of an engineer. The other thing that has to be found out is is RT. Now we shall find out RT by both methods, and then you decide which one is simpler. Let's look at this circuit again. What we have to do is Vs, then we have R1, R3, beta I1, R2. Let's find out RT by direct measurement across these terminals, looking back after killing the independent sources. Dependent sources should not be touched. So what I do is I short circuit this. That's the only thing that I have to do, isn't it? This is the only independent source, and killing it means that I short circuit this. I do not touch beta I1. Recall that this is I1. Now you see that as a result of shorting this, what is I1? I1 becomes equal to 0, and therefore beta I1 becomes equal to 0, which means that the current generator is not there. Alright, so what is RT then? It is a parallel combination of R2 and R3, because R3 goes to short circuit. R1 is ineffective, so it is simply R2 R3 divided by R2 plus R3. Okay. Now let's calculate it by the other method, that is by calculating the short circuit current. Our circuit, if you recall, is Vs, then R1, this is I1, R3, beta I1, R2, and I am going to short circuit this. This is the current that I want to find out, ISC. Alright, if this is short circuited, then obviously
Current in R2
ineffective. R2 is ineffective. No current in R2. Alright, and therefore ISC shall consist of two components. If we apply KCL now here, then this current minus beta I1 should be equal to ISC. Agreed? If I apply KCL here, this current, now what is this current? This voltage is Vs. What is this voltage? 0. It's connected to ground. Isn't this voltage equal to 0? It's short circuited, and therefore the drop across R3 is simply Vs. Therefore the current in R3 is Vs by R3 minus beta what is I1? I1 is still Vs divided by R1. This should be equal to ISC. That is, ISC is equal to Vs G3 with the same terminology, conductance, minus beta G1. This is ISC. Let's collect our equations. Is there any question here, this calculation? All we did was common sense. One application of KCL and the other is common sense, nothing else. We found out ISC. Let's write our equations again. ISC is Vs G3 minus beta G1 And what was Vt? Vt was Vs G3 minus beta G1 divided by G2 plus G3. And by definition, RT shall be the ratio of the two. What does the ratio give? 1 over G2 plus G3, which is precisely equal to R2 R3 divided by R2 plus R3. So we have been able to find out the equivalent Thevenin resistance by either method. Now it is for you to judge which method was better in this case. Which method was, yes? Direct calculation? Well, both of them are equally. In the first one it was much easier. Well, then it's a personal preference. I don't like green color. Somebody else likes green color, so it's okay. To me, both of them are equally easy. Once you see what's going on, once you see what the game is, then you can play the game according to the rules of the game. All right, and hope to win. All right. So these two fairly involved examples should convince you about the effectiveness of Thevenin's theorem. And along with Thevenin now, yes.
The problem that we did just now, had there been a dependent voltage source with voltage beta I1,
Yes, there could be a dependent voltage source.
so what would be the equivalent resistance then?
Oh, in the same example, you'll have to work it out. Beta I1 means beta Vs divided by R1, and you'll have to work it out. All right, let's look at this circuit. It's not a bad question. It's a very good question. What he says is R1, I1, R3, and he says let this be a dependent voltage source beta I1 instead of a dependent current source. Then we have an R2. What did you want to calculate? Thevenin resistance. But before that, you also want to calculate Vt, open circuit voltage. The open circuit voltage here obviously shall be equal to beta I1. All right. Now, if you want to calculate Thevenin resistance RT, what you do is you short circuit this. So R1 is ineffective. And if R1 is ineffective, then what is I1? I1 is 0. If I1 is 0, then beta I1 is 0. If beta I1 is 0, what does it mean? It means an open circuit or short circuit? A voltage source. If the voltage is 0, what does it mean? No, it's a short circuit. There can exist a voltage across an open circuit, but not across a short circuit. So this is a short circuit. So RT becomes identically equal to? What are you talking of? Who said 0? Who dares to say 0? I appreciate that courage, because it is indeed 0. Why? Because between these 2 points there exists a short circuit. Current has no compulsion to go any other way. It will go through the short circuit. That's indeed the Thevenin resistance. All right? Okay, so the problem becomes much more simplified if it is a controlled voltage source, dependent voltage source instead of dependent currents. In this situation, not necessarily in every situation. No, in other situations it may be more complicated. Now, along with Thevenin comes the name of Norton. Norton was an American working in Bell Telephone Laboratories, and he enunciated a theorem which goes by his name, Norton's theorem, which is precisely the dual of Thevenin's theorem. Dual. That means what Thevenin enunciated in terms of voltage, Norton enunciated in terms of a current. Thevenin's theorem says that the one port N is equivalent to a voltage source in series with a resistance. Norton says that N can be replaced by a current source in parallel with a resistance. All right, current source IN in parallel with a resistance which Norton preferred to call a conductance GN. All right, and the interpretations of IN and GN, you can very easily see that IN is nothing but ISC. That is, if you short circuit these two terminals, the current that flows to the short circuit is ISC, and you can also see that RN is nothing but what? If you measure if you measure the resistance looking from here, what resistance would you see? 1 upon Gn, and therefore Rn is simply equal to RT. Is this clear to you? The Thevenin resistance, the Norton resistance is the same as the Thevenin resistance. You recall, why is it so? You recall that in finding out Thevenin equivalent, we found out VOC, which is VT, we found out ISC, and we found out RT as VT divided by ISC. What we are doing in Norton is simply representing it in terms of ISC and an equivalent resistance. All right. Suppose I take ISC, which is VT divided by RT in parallel with RT, and find the Thevenin equivalent of this. We have a current source in parallel with a resistance. What is the open circuit voltage? Simply VT. If this is kept open circuit, then this current flows through RT. So VT by RT multiplied by RT is VT. And if you measure the resistance looking in this direction after killing the source, only source, it's simply RT. So Norton's theorem is simply another way of looking at the Thevenin equivalent. All right. What was considered as a voltage source by Thevenin is now being converted to a current source. So both of these problems that we solved also solves for Norton equivalent, because we found out RT is the same in both. In one of them it is a series resistance, in Norton equivalent it is a parallel resistance. The source is ISC, which we had to find for Thevenin equivalent also. For Thevenin equivalent we found out VT and ISC. Question may be that if I don't find the short circuit current, I know the Thevenin equivalent. All that you have to do is to divide the open circuit voltage VT by the Thevenin resistance RT, whichever way you find, it doesn't matter. And therefore whatever we have done for the two examples in finding out the Thevenin equivalent also solves for the Norton equivalent. And this leads us to a more generalization in the case of sources. That is, if we have a source V which is not ideal, which has a series resistance, let's say R, then it is a non-ideal voltage source. This is equivalent to a non-ideal current source of current equal to V by R, the short circuit current, and a parallel resistance equal to R. This is called source transformation, a big name, but a very simple application of Thevenin's theorem. Similarly, if I have a current source I, which is non-ideal, that is, it has a parallel resistance R, then this is equivalent to a Thevenin equivalent, a voltage source I times R in series with R. You will see that these simple transformations, the two transformations which go by the big name of source transformation, shall be extremely useful in solving network problems without loop analysis, without node analysis. In fact, Thevenin and Norton applied judiciously can save the labor of network analysis, however complicated it may be, and we shall see some examples next time. Is there any question? All right, then next time.